So now let's look at the elements of greedy algorithms. A greedy algorithm makes a sequence of choices. So it's a linear, right? So when we mention sequence, it means linear rather than a tree-like structure. So each of the choices that seems best at the moment is chosen. However, greedy algorithms do not always produce an optimal solution. Okay, hence the following things is in two ingredients that are exhibited by most problems that lend themselves to greedy strategy is, first of all, it has the greedy choice property. So what that means that in the earlier proof, we saw that if my greedy choice is not in my optimal solution, I can always find another optimal solution with that greedy choice. So in other words, you start with any optimal solution you are given, then we can always replace one activity with the one selected by the greedy choice. You still have a feasible solution, and because the one you are given is already optimal. So the new one is also optimal. The second one usually always true, which means that is optimal substructure. So from your greedy, from your solution, the subset of it is also a feasible solution, or the subset of it after you remove the greedy choice, the remaining selection will also be optimal for the remaining part of activities, right? So in other words, this is always pretty easy. It's pretty easy to see. For instance, I remove the first choice and then remove all the activities that are not compatible with it. In other words, they are conflicting with it. And then the remaining activities. So let's say A, M is the first one I choose. And then remove it together with all AK that cannot be chosen, right? So remove all of them. So whatever remains, and then whatever, so you have these activities, and then in your solution, in your optimal solution, after you remove AM, what's remain will be there because they are not conflicting with AM, and then those will also be optimal solution for the remaining activity. So that is called optimal substructure. So this is usually true. Hence, the usual thing to prove is to prove that the greedy choice property works. Okay. So using greedy algorithm, that is the one that we need to prove. Okay, so it's very easy to come up with a greedy algorithm to solve optimization problem, but it is not so easy to prove your greedy choice actually leads to optimal solution. So in other words, you have an optimization problem, I can find out a greedy algorithm to come up with a feasible solution, and then greedy choice property ensures that your greedy choice actually leads to an optimal solution. So let's look at one more example. So this is a coin changing. So let's look at the following example. Let's say at Costco. So this is a wholesale store. A hot dog and a drink at Costco cost $1.50, $1.50, and plus tax, Massachusetts tax, let's say, it's $1.59. So often we would give the cashier, if you have bills, two $1 bills, let's say, or maybe you have a $10 bills and so on. 5. So she needs the, let's say if you have, after the dollar bill was given, then it comes to coins. So how do you figure out the smallest number of coins as change, right? So in this case, the cashier will need to give back 41 cents as change. Generally, you'll never see that the cashier gives you 41 pennies. Rather, it will give you some quarters, and then dimes, and then nickels, and then the pennies. So the algorithm, obviously, is that you first figure out, you first choose the largest value, right? So for instance, we choose quarters first. So in this case, it's 1/4, because 41 is greater than 1/4, but 2/4 is already greater than 41, so you can have 1/4. And then it's a 41 minus 25, and then obviously you could have 1 dime, because you cannot have 2 dimes. If you have 2 dimes, then it's already 45 cents. So it's 1 dime. So that adds up to 35. So 41 minus 35 is 6 cents. So you're going to have 1 dime, 1 dime and 1 nickel, and then 1 cent. So that will be the ideal change. So how do we figure that one? Well, we already mentioned the greedy algorithm. Now we're going to say that we are going to prove that greedy choice works formally, right? So that's how we use it all the time. But then we can show formally that works. Given certain amount of change, let's say n cents, in our previous example, so that's 41 cents. Let's say in American systems, the denominations of coins are 25, a quarter, a dime, a nickel, and cent. How do we use the fewest coins to make this change, for instance? So what we talked about earlier is equivalent to saying this. Okay, so the number of cents n is, now we want to use a quarter first. So let's say we can figure out a quarter. So that will be 25 times A, and then B many dimes, 10 times B, C many nickels, 5 times C, and D many pennies. So add them up. So these, you add these up. So that is the number of coins. Okay, so we only look at the number of coins. They add them up to n cents. So what we want to do is we want this to be minimal, right? So we want to figure out A, B, C, D to make it minimum. This is a minimization problem. We can obviously try to use dynamic programming. As a matter of fact, we're going to use it here. So again, use the same old trick. So we first formulate the problem. So we want to say this is a coin change. I use DP to indicate that I'm going to use dynamic programming. And this I, so this I is a number of cents. The smallest number of coins whose values add up to I. So then if you have n cents given, so what we want to do is to compute coin DB of. So they come up with a recurrence relation. So this I value could be, so because we have 4 different denominations, so it's a 5, 10, 25, and 1. So first of all, we'll see if I is less than 0, and then it's impossible. So when it's impossible, we're going to just say, okay, this is big, very big. So that because we want to minimize it, so we want to make sure this is very large, you cannot minimize. If I is equal to 0, obviously there is no point to, there is no change, so the number of coins is 0. If I is less than 5, so which means that I now, because these two fails, which means I will be greater than 1, greater than 0, greater than or equal to 1, less than 5. So we got 4 pennies. So then we simply less I, at most I pennies. So you cannot use nickel. Otherwise, okay, so if I is equal to 5, it's just 1 nickel. And I is equal to 10 is 1 dime. I is equal to 25 is 1 quarter. So these are the easiest case there is. And otherwise, we are going to look at, okay, so which means now I here, we want to know whether we can use quarters. So then if we could, then I minus 25 is the remaining value. So if this is great, if this becomes negative, that means it's infinite. So then we cannot choose that. Okay? So if it's a greater than or equal to 0, that means we can choose quarter. And then, so we have this subproblem, choose quarter. If this becomes negative, then we choose dime. If this becomes negative, we cannot choose dime, then we will choose nickel. Likewise, we choose this. We figured out the minimum number of all these 4 choices or 4 subproblems. So we have 4 subproblems, and then plus 1 because we choose. So if this case is okay, then that's a 1 quarter we choose. If it is okay, then it's a 1 dime we choose. So we add 1. So that's dynamic programming. Come up with a greedy solution. So we always select coins with the largest value, as many as possible, as we said earlier. Okay, so that is the greedy choice. So we check, right? So if n is greater than or equal to 25, then we are going to recursively, so get 1 coin out. So increase A by 1 and repeat. Okay, so this is a new n minus 25. So repeat means we will check this to see if it is still greater than or 25. If it still is, we are going to subtract 25. Otherwise, then we're going down to move to the next one. So then finally, we add them up. That will be our solution. A greedy choice. So next, we're going to show that greedy choice property. We have the greedy choice property. So in other words, to show that greedy choice works. So in other words, we ask ourselves the following question. If we do not choose the largest point, is there a better solution? Okay, so that, because we have this denomination system, 25, 10, and 5, and 1. However, if there is a strange system, such as if you have in a weird situation that the denomination of coins is 10 cents and 7 cents and 1 cent, then our greedy choice will. So in other words, the greedy choice works. The denomination must be, for instance, this 10 will be multiple of 5, right? So 25 can be, it's a combination of 2 dimes and 1 nickel. In our case here, 10 is not a multiple of 7, right? You have a 10, 7, and 1. Then in this case, we don't have the greedy choice property. For instance, if I have 15 cents, Okay, so then if I use a greedy choice, so I will first use 10 cents, and then I will have 5 cents left. And then since that according to this denomination, we can only put 1. So then you got 5 coins here. However, if I don't use greedy choice, so I could have 7 and 7, 7, 7, 1. So this is optimal. Okay. So, um, so the greedy choice doesn't always work for some other denominations, right? So, but it works for this denomination. In some system, they don't have quarters. Okay. And I know there are some systems they don't have quarters. The Canadian and the American, they do have quarters. But some systems have 50 cents, 1 cent, 10 cents, 50 cents, right? They don't have quarters, but they have 50 cents. Now we're going to proceed to prove that greedy choice works for this denomination of 25, 10, 5, and 1. All right, suppose that S is an optimal solution, so which means that we have the smallest number of coins over the given change, so given n cents. So we're going to look at cases. Suppose that n is less than 5, so only coin denomination of 1 is applicable. So in this case, it's a trivial, so we can only count pennies up to 4 pennies. And case 2, now only coin denominations of 5 and 1 are applicable, so which means n is less than 10. So then if S contains a nickel, then we are done. Okay, because that's a greedy choice. Otherwise, that means now S contains n pennies. Then we'll figure out this is not optimal. So what that means is that we are comparing. So first of all, let n be 5 times d. Okay, so the optimal solution is 1 nickel is 1 nickel plus the remaining cents if we all use pennies. So n is equal to 5 plus d. So this 5 cents can be replaced by 1 nickel. So that means that obviously I should use this because 1 plus d is less than 5 plus d. So you must use nickel in order to have the smallest number of coins. Okay, so and there isn't any other way. So likewise, for case 3, only coin denominations of 10, 5, 1 are applicable. So which means that you cannot use quarters. If the optimal solution contains a dime, so that means that we are done because that greedy choice works. It has the greedy choice in it. Otherwise, we're going to show it cannot be the smallest. Okay, so in other words, this solution is unique. The solution here is unique. Unlike in the activity selection, the solution there, the optimal solution there isn't unique, but this coin change is unique. Okay, so if you don't select dime, so that means that you have this number of nickels because we choose nickels earlier, and which will be the following greedy choice will be C plus D. Okay. But then if you don't use dime, so let's say we don't use dime here, then we all use nickels. So this is the number of nickels. So which means we are not using, we don't follow the greedy choice. So C plus D C plus D is, okay, so this is the, so without, so this is a number of nickels, but now if we use dime, so with dime, then we have one dime, and then the actual number of coins is a C, so 1 plus C minus 2, because one dime is equal to 2 nickels, and then plus D pennies. And so we know that C plus D is greater than, so you add this one up, so that's C minus 1 plus D, because you minus 1 out, so this is not minimal solution. So likewise for the last case, so we can use, so these coin denominations are applicable, but we are not using quarters. So let's say we simply use from previous examples cases, we use dimes and nickels and cents. So we assuming we use B dimes, C nickels, and D cents. So that provides us an optimal solution. Now, since I can use quarter, so I can use 1/4. Okay, so that is equivalent to B minus 2 plus C minus 1 plus D. So this is the number of coins following. So this is the number of coins following the greedy choice. And then we're going to show that B plus C plus D, that's without. So it's without quarter. This is number of coins using quarters. So this is equal to, obviously, is greater than. So you add this one up. So it's a B plus C plus D minus 2. So this is the number of points using quarter, and this isn't. So obviously, then that is a contradiction. Maybe I will stop here, and we'll continue this topic in the next video.